I say it every single unit. If not, just know I say that, but then I teach everything like you haven't seen it, so it doesn't really matter. What makes an exponential function an exponential function? What about the exponent? It's a variable. You have a variable in the exponent. That's what makes this an exponential function. Now, the term that the exponent is on, what do we call that term? It's the base, the b value. So this b here is our base, and it determines whether we have a growth or decay function. Which one of these graphs right below here is a growth function? The first one, the one to the left. Why is that a growth function? Because as we read this graph, which remember we always read graphs left to right, as we read it, it is increasing. Therefore, we're going up, we're having growth. Versus if we have a decay function going from the left to the right, we're decreasing, we're going down, we're decaying. And I heard it right here, if we have a growth function, our b value is bigger than 1. But if we have a decay, our b is between 0 and 1, meaning it's a fraction less than 1. So like 1/2, 1/4, 1/3, 2/3. These are all bases that would give us a decay. Also in this function, we have what is called our a value in front of the exponential. This determines our y-intercept. This number will tell us where we're intercepting the y-axis. So let's go ahead and ask whether or not we have an exponential or not. So on part A there, if I'm looking at 3 to the power of x, let me grab the other stick. Is 3 to the power of x exponential then b? Yes, we have a variable in the exponent. Part B, is that exponential, Manissa? No, it is not, because we have -4, which is not a variable in our exponent. What about part C? Is that exponential, Alejandra? Yes, it is, because again, there's an x in the exponent. What about D, Evelyn? Yes. Even though it's a negative x, who cares? It's still a variable up there, so it is exponential. And lastly, Olivia, part E, is that exponential? So think about it. What does pi represent? Olivia? Yes, it is the number 3.14. So pi is not a variable. Therefore, E is not exponential. Any questions on how to determine whether we have an exponential function or not? It's pretty like cut and dry. Either there's a variable in the exponent or there isn't. Okay. Now I love this next part. We're going to work with an exponential function, and we're going to input different values and find the outputs. What we're actually doing here is we're trying to remember our exponent rules, which is something that we historically have a hard time remembering. So that's why we're going over it now. On part A, we're inputting 3 for x. So this becomes 2 cubed. is 2 cubed?
8.
8. 2 times 2 times 2 is 8. Remember, the exponent tells you how many times you're multiplying the base times itself. So 2 is being multiplied 3 times. 2 times 2 times 2. Next, we're inputting 0 for x. 1. Yes. Anything raised to the power of 0 is always 1. Always. So what's 10 to the power of 0? What's 100 to the power of 0?
1.
What's 0 to the power of 0? 1. 1. Always 1. 0 to the power of 0 is 1. Then, now here's where it gets interesting. If I'm inputting negative 2 in for x, how do I deal with a negative exponent? Yes, you create a fraction and put the entire term into the denominator. So I'm going to create a fraction. Nothing's being put in my numerator, so I have a 1. I'm putting this entire original term into my denominator, making the exponent positive now. And what is 2 squares? So this is actually 1/4. Let's just do a quick second example here because I know people get confused by this. If I had 4 to the power of -3, what should I do to simplify that? I create a fraction and I put 4 to the power of a +3 in the denominator. And I get, yeah. Any questions on the negative exponent product rule? Exponent rule. So then, this one's my favorite. I have 2 raised to the power of 1/4. Does anyone remember how we deal with fraction exponents? So the numerator represents our normal exponent. We can think of this numerator as the same as all the exponents we've done in the previous examples. It is just our normal exponent on the 2. Jeepers. Why is this being difficult? The denominator, however, is the degree of the root or the degree of the radical. What I mean by this is the 1 remains on the 2, but the denominator becomes a root of degree 4. So it's the 4th root of 2 to the power of 1, which is just 2. So it's the 4th root of 2. The should, I hate to say, I'm not going to say it. But you did have a whole unit over radicals as well. I was about to. So, if I had 3 to the power of 2/5, what does this become?
It becomes 3. No, wait. It becomes 5 to the square to the power of square. It's cube to 5.
No. Okay. Anybody else? Right. So remember, the denominator is the degree of the root. So we say it's the fifth root of 3 squared, which is how much? 9. So it's the fifth root of 9. Yes.
Is it like easy to write it that way, like the way you wrote it? So it's like 3 squared and 5. It's like split by line, so you write it 5. Like, is it easy to write it the way you did, like with like 2/5 like that, so that you can say that?
No, because that's not really telling you what operation's happening.
Okay.
Okay, so this part E is part C and D combined. We have a negative exponent and we have a fractional exponent. So let's try it. This becomes 2 raised to the power of negative 2/3. I would deal with the negative first. What does the negative tell you to do? It really doesn't matter what order you do. You should end up with the same answer, but I would deal with the negative. I said Ben scan first here. Good. To deal with the negative, we take the entire term and we make it the denominator with a numerator of 1, and our exponent is now positive. How do I deal with the fractional exponent? It is the third root. The denominator tells us the degree of the root, and the 2, the numerator, remains our exponent. And what is 2 squared? So I have 1 over the third root of 4.
Is it always 1 over?
Always.
So can there be a situation where it's not 1 over?
When the base is a fraction.
Okay. What would be able to?
So if you had this, what does this become? Let's do it step by step. Don't give me the final answer, but tell me, what do you think I should do first here? I think this is out of my view of my recording, so let's do that. Oh, shoot. Okay. What is the negative? How do I deal with the negative? I make the entire base the denominator, right? And now I have a positive 2. What is 1/2 squared? Do we normally like to see a fraction in a fraction? No. How do we get rid of the fraction in the fraction? There it is. We multiply the numerator by the reciprocal of the denominator. And what does 1 times 4 over 1 become? 4. So this whole thing, 1/2 raised to the power of negative 2, is 4. In your head, in my head, would I write all of this out? No. I would know that this becomes the denominator. I'm going to square it, so my denominator becomes 4. That goes into the numerator. Can you have our calculator, please? Yes. Any questions here? I know exponent rules just are slippery for you guys.
I have a question. What if it's a fraction and then it's like the exponent is also a fraction? Is that possible?
Yeah.
Okay.
Then you would have some sort of root.
Okay.
Okay. So let's now go ahead and create the equations based on this table. So we're being asked to create exponential functions whenever we're looking at a table set and we're trying to find exponential functions, you're looking for the amount that you're multiplying your y values by, your outputs by, to get the next y value. And it always has to be multiplication. Base is always determined by multiplication. For exponential. So how much do you multiply 4/3 by to get 4? 3. How much do you multiply 4 by to get 12? How much do you multiply 12 by to get 36? 3. If this number ever changes, so say it was times 3 and then you had a times 4, that would mean you do not have an exponential anymore, and you cannot create an exponential equation. The amount you're multiplying by has to stay the same each time. In our equation, what do you think the 3 represents?
The exponent.
The base that has the exponent. That 3 is our base value. What goes on the base? X as our exponent. What is the last value you think I need to find? The y-intercept, which is determined how? How can we find it on this table? When x is 0, that gives us our y-intercepts. So in f of x, what is our y-intercept? 4. So I just write a 4 in front and I'm done. That's it. Find the amount you're multiplying by and find your y-intercept, and you have created an exponential equation. You guys work with your groups and find g of x and h of x. So both found our y-intercepts. On g of x, the y-intercept was 8. H of x, the y-intercept was 3/2. We found our basis by knowing what we're multiplying the y values by each time. And yeah, both have a x in our exponent on the base. Now, g of x and h of x are both what type of exponentials? Decay. They are decay functions because our b value is a fraction less than 1. So they're decreasing, which we can see, yeah, they're going down. They're going down. All right, so now for the fun stuff. Whoops. Where's my undo? Right over here. So now we're going to graph these. Now I'm going to change this first one. So if you already started graphing, I'm so sorry. I'm going to change it to be this. Why do you think I'm changing it to be just 2 of x? I want to show you guys the parent function first. Now, 2 raised to the power of x is a parent function. 3 to the power of x, what is that? What if I change the base from a 2 to a 3? What transformation has happened there? It's a trick question. It's also a parent function. Changing the base does not determine a transformation. Changing the base just creates a new parent function. So if I had 100 raised to the power of x, that's also a parent function. You never, if it's ever asking you for transformations, you never state the change in base. Okay? So yes, we're going to go ahead and graph 2 raised to the power of x, which is a parent function. Now, like I said at the beginning of class, we're going to be graphing without a calculator. What do you do when you're confused on how to graph? Plot points. And how do you find those points? You create a table. You plug in x values to get your y values. Now you can do this in your head, but I've seen a bunch of people today and yesterday drawing tables, so I'm going to go ahead and draw a table just so you can remember how we do this. So give me a value you'd like me to plug in first.
1.
So normally most people start with 0. If I plug in 2 to the power of 0, what do I get? So I'm going to plot the point 0, 1. What number would you like me to try next?
1.
When I plug in 1, what do I get? 2. Give me another one. Ooh. That's going to be a hard graph.
3.
I would do 2. 2 to the power of 2 is 4. So I'm plotting the point 2, 4. And I think that's good enough in the positive direction. What do you think I should do now? I would go in the negative. When I plug in a negative 1, remember, what do we do to deal with negative exponents? Put it into the denominator with a positive version. And then 2 to the power of 1 is just 2. So this whole thing is just a half. Meaning I'm plotting the point negative 1, 1 half. I'll go one more into the negative. When I have a negative 2, 2 to the power of negative 2 becomes what? 1/4. Good. 1 over 2 squared, which is just 4. So I have negative 2, 1/4. What do you see is happening here?
It can never touch the y-axis.
So it's approaching a what? What is that thing called? Yes, it's approaching this asymptote here. What is the equation for that asymptote? Y equals 0 is our asymptote. All exponentials will have a horizontal asymptote. Asymptote. No, only one, and it has to be horizontal. So then I'm just going to connect my points. I know that to the left here we're approaching our asymptote, and to the right we're exponentially increasing. That's my parent function. Now, as I change the base, the parent function does change. The way that it changes is by telling us the second perfect point. So all parent functions will go through this point that is up 1 from the asymptote. The next perfect point after that depends on the base. So here, because my base was 2, from my, you can think of it as center, I go up 2 over 1. If the base had been 3, what do you think we do to get our next perfect point?
Up 2.
If our base is 3, up 3 over 1. What if my base is 10? Up 10 over 1. But all of them still go through this very special point that's just up 1 from the asymptote. Okay? Let's talk about the attributes. Attributes, attributes. I never know which one it is. Okay. What is my lowest x value? I think this is Griffin. Yes, because I'm trying to find my domain eventually. So what's my lowest x, would you say?
0.
X value. There it is. And what is my max x value, Alex? Positive infinity. And what goes next to both of my infinities? Anybody?
Parentheses.
Because you cannot be infinity. Good. What is my lowest y value? Nobody. Aaron. 0, yes. And can we be 0 here? So what goes next to 0? And what's our max y value, Darren? Positive infinity. Your exponentials will always have a domain of all real numbers. Range will not. The range changes based on where the asymptote is. Nazarene, what is our intercept? Right there. Beautiful. It's a y-intercept. And let me just ask in general, what are the transformations here? None. It's a parent function. Hasn't been translated, hasn't been stretched or compressed or reflected, so we say none. Where's our asymptote, Declan? Y equals 0. What is our first end behavior statement, Sam? Oh, shoot. Oh, that's right. Man, my days are just getting... Okay, so Madeline, there you go. As x goes to... Yes, you chose the harder one. But I love that you chose to do goes to negative infinity first. That's the statement that I would have written first as well. I always like to go to the left first, and then I go to the right. And then what's our second end behavior statement, Sebastian?
As x goes to positive infinity, y goes to positive infinity.
Exactly, yes. Right. As x goes to positive infinity, y goes to positive infinity. Any questions on how we found those attributes? Okay. I want you now to work with your groups and do graphs 2 and 3. Go ahead and do graphs 2 and 3 and write down all of the attributes. Before we graph log, we're going to go ahead and graph this exponential just really quickly. What do we know about this exponential? What can we immediately graph?
0, 1.
0, 1. Oh, okay, yeah. What else can we immediately graph? The asymptote is what I would have started with, but I mean 0, 1 is perfectly fine. I know that this hasn't been moved up or down because there's no k, so my asymptote is still y equals 0. I plugged in 0 and got 1, so that's how I plotted that point 0, 1. What happens when I plug in 1?
10.
You get 10, so we have the point 110. And I know that to the left it's approaching my asymptote, and to the right we're increasing exponentially. And that's enough. Why do you think we graph this first when I'm trying to eventually graph log? It's hard to tell who's talking because of math. Oh, okay. You weren't even having math class. Oh, okay. All right. We graph log first because we graphed exponential first because exponential is the inverse of log. This is what the paper last class was trying to get you to realize, that log and exponentials are inverse functions. They're inverse operations. So, knowing this, looking at this log we're trying to now graph, what is the base on that log? 10. If there is no base given, there is an invisible base of 10. Always. If there is no base given, your base is 10. So that's why these are inverse functions. If we instead had an exponential of 2 raised to the power of x, what would the inverse function to that be, do you think? Log base 2 of x. Good. The bases have to be the same for them to be inverses. Now, how do we find an inverse on a graph? Yes, we're switching x and y. We're reflecting over the line y equals x. So, if I had an asymptote at y equals 0, where is our asymptote for the log? X equals 0. If I had a point on 0, 1, where do I have a point for my inverse? 1, 0. If I had a point at 1, 10, where do I have a point? 10, 1. This is our log function. It is reflected over the line y equals x. Now, we still haven't really talked about what log is, and this is the part I love. If I'm looking at a log, all that it is an operation. It's asking a question. Way back when log was created, and yes, log was created, mathematicians, as we know, or as we should know, are lazy. They're super, super lazy. Log is just asking a question, a big, long question that mathematicians were like, we're not going to write that question every time. We're going to shorten it. Let's choose the word logarithm because it sounds fancy and makes it sound smart. And so they shorten this big, long question to just the word log of base of a value we're logging. All that the question is, what log is asking. Log, the word log means what power. And then we look at the base and we say, do we raise whatever the base is, in this case 10, to equal x. So this super short log base 10 of x is actually asking, what power do we raise 10 to equal x? So if I input a 1 for x, I'm asking, what power do we raise 10 to equal 1? And what would you tell me? 0. So log base 10 of 1, what power do you raise 10 to equal 1 is just 0. And we have now done log in our head. What about, and actually that's this first point, right? 1, 0. What about when I input 10? What power do we raise 10 to equal 10? 1. So we've now found this second point, 10, 1. That's all that log is. It was created to ask the question, what power do we raise 10 to equal x? What power do we raise the base to equal the argument? All right. So
I have a question.
yes.
Will we also do like a natural log?
Mm-hmm. Not so much today, but more on the application stage. Now, I'm not going to go over these attributes because I feel like we've gone over, or we know how to find attributes very well. I will just ask, is this graph increasing or decreasing? It's increasing from left to right. So when I ask for decreasing interval, what are you going to say? None. And we're increasing from where to where? Oh, look. We have a what? So we start increasing at 0 to infinity. And it's parentheses because two things. We can never be the asymptote, and also because we're never increasing nor decreasing at a single point. Yes. The what? The end behavior, sure. So remember, there's always two ends. Just because I don't go towards negative infinity doesn't mean this doesn't have a left end. Our leftmost end, what x value is it approaching? It's approaching 0. So I say, as x goes to or approaches 0, what does our y value approach? Negative infinity. And then the other statement is like normal. As x goes to, what does it go to the right? Positive infinity. So as x goes to positive infinity, y goes to where? Positive infinity as well. All right. So let's try graphing this, one of these. Like I said, we're going to do this first one. I may talk a little bit about the second two in case you're confused, but then the following three, the bottom three, are your homework. And also notice the last one is ln of x, or natural log of x. Does anyone know what natural log, what is another way we could represent that? I think I heard it. Log base e of x. That's what natural log is. Log base e of x. Okay. Well, let's graph this one first. Now, there's two ways you can graph it. Either you can be super confident about log, which hopefully by the end of this unit we will be super confident, or you can think about what the inverse function is going to look like and then reflect it over y equals x. So either you can graph immediately log base 2 of x, or you can graph the inverse of this, which is 2 to the power of x. Which one should I show you?
So it's log, so it's easier. So I already know what 2 of x is.
So just know that you can, on your graph, quickly sketch this and then just flip all of the points. Now, let's go ahead and try to do this just knowing what a log does. Remember, log asks the question, what power do we raise 2 to equal x? Now, we know that this has not been moved left or right at all. So where is our asymptote? X equals 0. Now, what do you think is the easiest number to plug in for x on a log? So you don't want to plug in 0 because that's asking the question, what power do you raise 2 to equal 0? the asymptote. That's why the asymptote's created. Because you can never raise a number to something and have it equal 0. Can't happen.
How about
So,
that?
1. 1 is the easiest number to plug in. Let's do it here. So I'm plugging in 1, meaning I'm asking what power do we raise 2 to equal 1? 0. So I'm plotting the point 1, 0. What do you think is the next good number?
2.
Let's plug in 2. What power do you raise 2 to equal 2? 1. So you plot the point 2, 1. Give me a next perfect point input number.
-1.
Can't go negative because of the asymptote. 4. If we plug in 3, can you raise 2 to anything to equal 3? No. But you can raise 2 to something to equal 4. What is it? So I'm plugging in 4, and I'm asking what power do we raise 2 to equal 4? And what do you tell me? 2. There's actually one more point that'll fit perfectly on here. What input value do you think that is? 8. What power do we raise 2 to equal 8? 3. 8, 3. You do not need that many points. I just liked giving you log practice, okay? 2 points probably was enough with the asymptote. 2 points in the asymptote. Yes.
What if the asymptote is like very, very like off the graph?
We wouldn't give that to you because there's no point in graphing it,
Okay.
right? Or, like I was saying before, we could have known how to graph this 2 to the power of x. We would have graphed our asymptote at y equals 0. We know it goes through 0, 1, and we know it goes through 1, 2. And then we would have graphed that, flipped it over the line y equals x, and graphed our log. Is there anything else I wanted to say about these 2 graphs? Oh, let's just quickly look at this one, because what do you notice about the first graph versus this third one? It's translated down 4. So what can we do? Oh my God, take the first graph. It has the same asymptote, but every single one of these points is now moved down 4. So from here, I'm moving this point down 4, and I plot the point 1, -4. I take this next point, 2, 1, and I move it down 4. I take this point, 4, 2, and move it down 4. And that's probably good enough. And boom, I've graphed it. All right. So if the intercept is off of the graph, we're not going to make you state it. All right. Technically, the intercept here is 16, 0. You won't know today how to find that algebraically without a calculator. We'll learn how to do that next class.